Hello, this is Semantic Web Technologies, lecture number 3, Semantic Web Basic Architecture 2, part 4, How to Query RDFS with SPARQL. In the last part of the lecture, I have showed you how to query RDFS statements and RDFS databases with the SPARQL query language. And today, I want to show you the future of SPARQL, which has become almost a standard, but of course, there might be some changes, although we have reached a stadium of a proposed standard for SPARQL 1.1 since November 2012. So this is almost complete. So what's new with SPARQL 1.1? There are several new features. There are features that concern the query with SPARQL, and there are some different features. For example, SPARQL becomes a fully fledged data manipulation language with a SPARQL update function. So in future with SPARQL 1.1, you can not only query RDF data, but you also can manipulate and update RDF data. And on the other hand, as a fourth part, SPARQL 1.1 also enables entailment for RDF, RDFS, OWL, and also for RIF, which is the rule interchange format. So it means there will be logical inference mechanisms and logical connections, logical relations will to be taken into account when answering a SPARQL query. So this is for the future. Right now, we want to concentrate on the new features that SPARQL query in SPARQL 1.1 provides. So let's take the first example. SPARQL 1.1 allows assignments of new variables. So this was not possible to create new values on the fly within the query. So look at this simple example. Here we have some data, some beverages. So we have lemonade and the price, and we have beer and the price, and so on and so on. And what I want to select in this new SPARQL 1.1 query, I want to select items, and I want to assign the items a new price, which is 10% higher than the price that is given in the database. So what I do here is I can formulate a select statement where I can compute a new price here with a variable PR multiplied by 1.1, and I can take this as a newly created variable. And in the answer table, you see the result where we have all the new values for the variable new p computed and already available here. So you only have to take one thing into account. You only can use variables that are not bound until the time when the statement is written. So this doesn't hold, or this does not work for already bound variables. So, but this is pretty clear. Okay. Another example are aggregate functions. You know aggregate functions from SQL, from databases, for example. So aggregation functions, on the one hand, are able, for example, to count the number of results, to group results, and to group results and to compute constraints upon these groups. And we start with simple counting argument. For example, here what we want to do is we want to count the number of items in the database. And you see here RDF statements for 5 types of beverages. So we have a price, and we also have a type of the beverage. And in the statement itself, in the select statement, you have the new aggregate function count. And what you count is the number of times the variable item is assigned to a value from the database, and you select this here also as a new variable C. And the result will be simply a number, because all the results simply will be counted that qualify for the basic graph pattern that matches here to the RDF graph here. And the result will be 5, because, of course, it's 5 different beverages that are counted here. Okay, let's take at a little bit more complicated example. So for example, what we have here is we want to count the categories of the beverages. As you can see here in the database, in the gray box, you see we have a lemonade, a beer, and we have 3 types of wine. And what we want to count is the number of distinct categories. It means soft drink, beer, and wine should be 3. So how do we formulate this in SPARQL? Pretty simple, of course, we want to count. Therefore, we have the select and then the aggregation function count. And then we only want to take into account distinct types. So we say distinct as a keyword and then the variable for the type. And then we say we select this as a new variable called z. And we have to only match those RDF triples that match here the basic graph pattern item has RDF type T. So what we do here is we select the different types and the distinct keyword therefore results that we only have distinct types count. So the result will be 3. Okay, what we can do next is we can restrict the things that we here group with the keyword group by. Group by is also taken from SQL database query language, and it works in the pretty same way. So what we do here is we want to count all items per category. So you see here we have 3 different categories. We have 2 categories, lemonade and beer, with just 1 item in it, and we have a category with 3 items, wine here. So we want to count how many items are in each category. Therefore, we group the results by the categories. So this is group by T. And T is the variable that holds the category according to this basic graph pattern. And what we do next is simply, okay, we again count T. We select T, which is the type or the category here. And for each T, we count all items that belong to T. So the result will be this simple table consisting of the name of the types and the number of items belonging to the type. What you can also do, for example, is you can also use here the keyword distinct. So you count simply distinct items, and then you would have the number of distinct items per category. Here in the next example, we go one step further. We only want to have in the result those groups or those categories that have more than just 1 item in it. So we say, in respect to the grouping, we only want to have those groups in the results that fulfill the requirement or the constraint that is placed after the keyword having. And there we have having count item larger or greater than 1 means that we count the items of each category and only take those into account for the result where there is more than 1 item in the result. And the rest of the query is as the query before. So therefore, this having count item greater than 1 simply serves as the filter and filters out all items or all categories that contain 1 item or less. So the result is given here. You have a simple table with 1 row as a result, and there is wine as it has 3 different items in its category. Okay, SPARQL 1.1 provides more aggregate functions. Besides the count aggregation function, we can also sum up numericals with a sum keyword. We can compute an average sum also of numerical values. We can compute a minimum or a maximum value. This can also be applied to strings. And we have 2 interesting things that are quite new and that are maybe not known from SQL. We have one thing that is called sample. And sample is a function that picks 1 element from a number of elements or from a group in a non-deterministical way. So you will have a pick from a larger group of items. And at last, we have a thing that is called group concat, and this means all items in the group will be concatenated with a designated string separator that has to be given for concatenating those single items. So let's look at the example. What we want to take here or want to make here is we have given a small knowledge base with 3 different persons, given as a 4th person. And for these persons, we have several information. For example, we have 1 or more 4th names, which are the official names, and we have several nicknames for each person. And what we want to have is we want to have a result list where we pick one of the official names, no matter which one, And we want also to pick out all nicknames. And we want to connect all these nicknames in a comma-separated list. So how do we do this? It's just simple. We prepare our select statement and we say we want to have in the result just one arbitrary official name. So we pick one of these names with the aggregation function sample. And as a second part, as a second column of the result table, we want to have a list, a concatenated list of nicknames that are separated by the comma. If we look at the graph pattern, we see here that we select person. So we select in the variable p, which is a fourth person. And for this person, we select the fourth names in the variable n and the nicknames in the variable m. And via the aggregation function sample, one of the official names will be picked for each person, and all of the nicknames will be concatenated here. And the result is, as you see here, a simple list where we have here a column with one arbitrary name, so one name picked from the official name list, and a concatenated string with all the nicknames of the person separated by a comma. Okay, let's look at the next example. One thing that we are able to do in SPARQL 1.1 are so-called subqueries. You may be already familiar with subqueries from SQL, so it's the same in SPARQL. So here now you will be able to place a SPARQL query in the part where you have the basic graph pattern matching. So let's take a look here at the example where we have a sub-select. So what do we do here? So what we want to have, we want to select book titles, which is the T, and only those book titles of books that are from co-authors of me. So how do we do that? Okay, of course we want to select titles. Where? And then we have here D, which is a person, which is the maker, or which has the maker P. And from this we want the label. So this is the title of the book. D will be the book, T will be the label or the title of the book, P will be the author of the book. Then we say here in the subselect, in the graph pattern matching, select all distinct Ps, so all distinct makers, authors in that case, that fulfill the following condition, that, for example, here have as an author me, this is my URI, and in the same hand, we should filter them in the way that, of course, we want only those that are not like me. So we have here where P is not equal to my URI. So this will be all authors that together with me have written a book. They will be in this variable P. And I filter them in this filter string where I say, okay, the co-author should not be my URI myself. So therefore, I will get as a result all book titles that have been written by co-authors of me. And the result, as stated here for a subquery, always is achieved by first evaluating the inner query and then evaluating the outer query. Another thing that is also new in SPARQL 1.1 is negation. So what you can do here is you can refer to conditions where an answer exists or does not exist. So for example, what we want to do here is we want to make a small select statement on a database that we have given here where we have 3 people in it, and for one people, for Alice, we have the name and we have the type, which is a person, and for the other persons, we simply have the type, we do not have the name. And for example, if we want to select all persons from a database where one specific attribute is not available, for example, they don't have a name, then we can do this with the filter expression not exists, and we say filter not exists, and what should not exist is a name or a triple that has a 4th name in it. So with this simple filter mechanism not exist, I can filter out results and can say can give specific conditions for things that should not be provided in the result. So for example, here only Bob is in the resulting table. Another new operator is the minus qualifier. It works in the same way here. So what we do here in this little example, if you look at it, we have, again, a database given with persons. And for the persons, we have a given name and a family name. And we have 3 persons in it. And what we want to select here is nothing else, but we want to select all triples, but not triples that fulfill the following conditions. We do not want to have triples where the given name of any resource here or any subject is Bob. So in the result will be only triples where the given name is other than Bob. So it's Alice and it's Carol, and Bob will be neglected in the result. So these are a few new functions that are provided with SPARQL 1.1. Just one thing I also want to mention to you, which is new in SPARQL queries, SPARQL 1.1 queries, and it's the so-called property path method. So with property paths, you will be able to navigate within the RDF graph and to formulate property path expressions for matchings on that graph that will be much more complicated and much more comfortable, on the other hand, than questions or queries that have been possible before in SPARQL 1.1. So for example, you can define a graph pattern or a property path of different lengths. So for example, the trivial case is if the path length of the property paths, you connect property and properties, is only 1, then you have a trivial basic triple pattern. So this is nothing new. But on the other hand, you can, for example, you can define possibilities. So select things that fulfill either this or this condition in the graph. So this can also, of course, be achieved with SPARQL 1.0. But on the other hand, you really can define sequences of properties. So for example, you start with at a resource X, and then you follow the property fov knows, and again, on these resources that match the first triple, you also match the next fov knows and the next fov name. So you will have, in the end, people that are known to people that you know. So you see, you go one step further in the graph, and what you previously could have done with several connected SPARQL queries, you can do here in a single SPARQL query with so-called property paths. So you connect one property, another property, and another property, or even more, to property paths of the length greater or bigger than 1. On the other hand, you also can, for example, put into these paths reverse properties. So you reverse the direction of a property. So for example, this is a basic graph pattern. For example, X has the fov mailbox, and then is the name for the mailbox. You can reverse this property, fov mbox, with this little sign here, with this little angle. And then this can be read reversed. So this is the object, this is the property, and this is the subject. And then in the end, you also can connect sequences and inverse properties. So you will have inverse path sequences. So for example, you start here with a resource, you look at all the things that are connected to this resource via fov knows, and then you're looking backwards. So you have the reverse fov knows, and look who knows or which people are known by people that I know. And now I filter this expression and want to exclude myself or the people themselves, and then I will get a list of people who know people that are known by them. So this is quite interesting, and you can play around with it. On the other hand, if you do not know how long the graph will be, you can also, for example, define something like a transitive graph pattern, a pattern of arbitrary length. So with this simple plus sign, you say that there is at least one fov knows or many fov knows, and you follow as many fov knows as there are available. And you can here make a short matching expression that traverses a whole graph with the fov knows property. So this is really pretty interesting. And on the other hand, you also have the possibility to negate a property path, and you say in the answer you want to have only those results that do not contain properties of this type or connected properties of this type. So you see, SPARQL 1.1 is pretty much more complicated than SPARQL 1.0, and it gives a lot of more opportunities and things that can be computed with it. So the standard is not now finished, but it will be soon finished. So In the end, there's much more to come, and on the way there are many implementations also of SPARQL 1.1 that you can play around with. Okay, so much for SPARQL and SPARQL 1.1. In the next part of the lecture, we want to concentrate on the question, how should we store the RDF data, where we put then our SPARQL processing on it. So how should we store RDF data? Should we use a conventional database, a relational database, or are there alternatives? So we will go deeper on that question in the next part of the lecture.